So I would like to start by joining all the thanks, because I'm also I'm very grateful for this conference has been organized. It's great to be able to do that again, and also to, of course, thank the local people who allow us to be here on the island. I love the telescope, I must say. I don't go as far back as you quite, but my first one was in '96, and I think I've been here a few times per year ever since, and I really love the Nordic telescope, I must say. And I love observing with it in all the different modes, and I love the people, I love everything about it. So first let me say just a few words about other things. I mean, so the NTE is an instrument that's built by a consortium with many partners, so this is just a list. I mean, we are not just people in Copenhagen, luckily. There are contributions from, there's also from Aarhus, from Turku, Helsinki, Iceland, Sweden, Stockholm in particular, and then major contribution from Milan, Heidelberg. They have made our controllers for the near-infrared. So there's a long list of contributions. It's not something we're doing alone. The major funding is coming from the Carlsberg, so that's where we got funding for most of the hardware from the Carlsberg Foundation. So please drink some beers from Carlsberg. So okay, and then I want to say just the team. So this is sort of a list of some of the people in the NTE team. In particular, I think there are many names here, but I think in particular I should mention Mikael Andersen. You'll get to hear from him in a few minutes. Anton Sørensen, Jonas, who's also here, and Jakob. Those are the ones who are really working very, very hard on this instrument. I've been mainly working on trying to get funding. That is what I have tried really to work on. I'm not an expert in instrumentation. So, then I would like to say a few words about my own motivation for engaging in this project. So my personal interest is sort of galaxies. Studying galaxies, in particular galaxies at high redshift. That is what I also worked on in my PhD, and that's what I still find interesting. So I think galaxies are very fascinating objects. I mean, as objects seen, as a phenomenon. I mean, to understand those, we have to learn about, of course, normal stuff, baryons, gas, stars, metals, dust, dark matter, supermassive black holes. It's all those things together. And it's not something we can understand in isolation. It's also, they're not sort of isolated systems in the same way as a star is to a higher degree. They talk a lot with their surroundings, so we have to understand stuff coming in, stuff going out. And like stars, there's also a lot of scaling relations that are becoming more and more clear. People talk about the main sequence as they do for stars, and there's also scaling relations between mass and metallicity, star formation rate, luminosity, all these things we have to understand. And a very powerful way to do that is to use absorption line studies, as I'm sure everybody knows. So I've started out in my PhD to work on quasar absorption line systems. So that's where you use quasars, not as something interesting in itself, but as a light source, and then you look at the absorption imprint from something in the foreground on the light of the quasar to study dynamics, metallicities, dust of this foreground object. And while doing this at the Nordic telescope, I also got involved in gamma ray bursts because I was also triggered many times while I was observing these quasar things. And then I got into to gamma ray burst work because it's very, very similar. I mean, the thing you can do with quasar absorption lines, you can also do with gamma ray burst, sort of in a complementary way. So that quickly became very fascinating to me. So I also got into that. So we can study a sideline for something in the background, but you can also look at something exploding inside a galaxy, and then look at the absorption imprint of that. What happens when that light goes out of the galaxy? So that's an independent way of doing the same. All right. So that's sort of my. So this is just an example. You can get very, very detailed information about absorption lines from. In this case, it's just some quasar absorber. You can measure very detailed abundances, and you can look at dust depletion. You can look at what is the velocity information. Extinction. There's a lot of information that you can get out from objects you cannot really see because they may be so faint that you cannot see the light itself of that object. All right, so that's just my personal interest. All right, is that time? So then I want to get to the motivation for the NTE. So working on gamma ray burst, it was very clear that the knot very clearly stood out as something that is great for transient work because, and we'll hear more from Daniele in the afternoon. I mean, I think what is important or has been important is the flexibility of the community. I mean, there's a very informal way of engaging with each other, and it's a very friendly community, very good instruments. But there are some very important limitations, which is then why we want to think about this new instrument. And that is, there's only one instrument that is, I mean, for this kind of work, always available. That's StanCam. So FIES is really not, it's extremely rarely that there would be something where we could use FIES. So we have StanCam as something that is always there. But of course we cannot do, that means we cannot always do spectroscopy with a knot. And furthermore, the spectral resolution of ALPHOSC, which is sort of the instrument that is most of the time available, that is good for measuring redshifts. We can also measure hydrogen abundances. We can also get some information about extinction, but that's about it we can do for these gamma ray bursts at least. I mean, so the amount of information we can get out is limited by the resolution. And the spectral range, because of course this is only optical, and so that means what about the near-infrared? So near-infrared imaging and spectroscopy is very rarely available when there is a new transient source, like a gamma ray burst we want to study. So that was I would say the major point. The resolution and this absence of near-infrared capabilities as a standard thing. So, and then the major motivation, that is, I mean, what could we do? Then the inspiration for what to do was X-Shooter. So X-Shooter was an instrument, many of you, I'm sure you know X-Shooter. That is an instrument at the VLT. And Michael was instrumental in developing the concept for X-Shooter. And that really was the inspiration for NTE. How can we do something similar? How can we make an instrument like or preferably improved, like X-Shooter for the knot? So that is what the NTE is. That is our attempt to give the answer to that question. How can we make something similar to X-Shooter for the knot that is improved? And Michael will go into much more detail about how it is improved. Okay. And then some additional constraints we have for NTE, unlike what is the case for X-Shooter. X-Shooter is sitting on the VLT with 13 foci or whatever it is, so you can always switch to some other instrument. That's not the case at the knot. We want to have, I mean, to reach the goals I mentioned, we want to have this instrument available where there's some important source we want to observe quickly. We cannot wait for an instrument change. So we want it to be at least quasi-permanently mounted. It may be that there's a small fraction of the time where something else is on, but it should be a rare thing. In general, it should be there when there's a transient source so we can use it. So that means that this instrument should also fulfill most of the needs of the community. Not only the transient community, but also the other part of our community. They should feel that whatever they could do before, they can also do now, and preferably be better than they could before. So that is very important that the users feel that this is an instrument they really want to use. And they don't wish to change it and put something else on. Most of the users should feel that this is what they want to use. So we want to have imaging, preferably with the same field of view as available now, and filters, some polarimetry, and so on. So we try to fulfill most of the needs of the community with this one instrument. And then preferably, of course, it should be innovative, and it should give our community some competitive edges. That's, of course, also something we think about. How can this be something that strengthens the use of the knot for the next 10 years? All right. Then I just want to motivate a little bit from the side of science that I was asked to do. And so I want to say a little bit specifically about gamma ray burst. You can say, okay, now people have studied gamma ray burst afterglow since 1997. Hundreds of those have been studied with the afterglow. So why do we want to do that still? I mean, isn't that a done field? Is there anything worth doing still? You can say. So and that is the answer to that, yes, there is a lot to do. And that's why we want the near-infrared capability. That is really because there is, especially two areas where I think we have, there's a lot of things we haven't done with gamma ray bursts, which I think will be very interesting. So, and I'll mention three things. I think Daniela will go into more details as far as I can see from the title. But very high redshift bursts is something but there still is a lot of potential. I mean, we know they occur roughly 1 or 2 times per year. There is something at redshift beyond 6. And they can offer a very clean measurement of the ionization degree of the intergalactic medium. So that's something that I think that is still a lot of potential in doing that. Then there is something I was interested in from the beginning of this afterglow study. That is, there's a large fraction of the gamma ray bursts where we don't find an afterglow. And they're called dark bursts for that reason. And that has been refined, and now there's some more clear definitions of what is a dark burst. But that's very clear that there is a significant fraction of the afterglows where we don't, of the gamma ray bursts where we don't find the afterglow. And so they're sort of unstudied. We have at least much less information about what kind of environments do they come from. We just have some hints, which I'll try to give some examples. And then, of course, there's the third or whatever of the gamma ray bursts that are short. Now we know that they are related to neutron star mergers. At least some of them are. And they release some optical light, which is called a kilonova. And I think Daniela will talk about that. But that we only have one spectra of those so far. So I think that's, of course, we want more of those. So just to mention just a few of those things, I would like to start with this issue of these so-called dark bursts. And that we know a lot about where they come from now, because people have been very careful and built sort of complete samples, and that means also to try to say what can we say about those where we didn't find the afterglow by looking at the host galaxy. And this is a plot showing from Perley 5 years ago, Perley et al. So this is looking at redshift, and then it's the brightness of the host galaxy. So this is this axis here is the host galaxy. These are very bright. These are very faint dwarf galaxies. These are hugely, enormously bright galaxies. And then there's a color code. You can see green means this is where there was sort of a normal afterglow, something that was not obscured, and red means obscured, dark. That's where those we typically don't find the afterglows. And you can see those things where we typically don't find the afterglows, they're coming from big, bright galaxies. So that's because they are in very metal-enriched, very dusty systems. That's why we don't see the afterglow. So all this information we have about metallicities and dynamics and so on from afterglow spectroscopy is from this sort of, at least by far the majority is from these faint galaxies. Low mass galaxies, low dust content. So we have an incomplete picture of these star-forming galaxies using this method, and there's a sort of a potential up here to try what can we say about these environments, which is something that hasn't been done very, very much. I'll just show a few examples, because there are a few examples where it has been possible. So this is a very fantastic spectrum. This is a spectrum of a gamma ray burst, redshift 3, that was taken with the Keck telescope, because some of the, I think it was Perley, was actually at the Keck telescope, and when the burst went off, he was triggering immediately, so they got the spectrum 12 minutes after the burst, so while the afterglow was still bright. And they got this spectrum, which is an amazing spectrum. This is H1, this is hydrogen, and then it's also full of H2 lines, so that's molecular hydrogen. This is not noise, this is metal lines, so it's just full of metal lines, very high metallicity. And it's reddened, so you have the 2175 angstrom bump, so it's very reddened by 3 AV of 3. So this is probably sort of an example of what we are missing. That's that kind of system. We tried to observe it as well with the VLT, but we had to wait for it to get dark in Chile, but then it was gone. There was nothing left. I don't know, I remember 5-6 hours later, there was nothing. This is a spectrum from the NUT, actually. Well, it's something similar. So this is you see, we only got an alpha spectrum, but that alpha spectrum is basically just the 2175 angstrom bump. You see this big hole here? That is do everybody know the 2175 angstrom bump? That is this feature in the extinction curve of the Milky Way. So that is very clear also in this. You see this bump is dust. Normally this would have been a power law going up, so it's strongly reddened by dust in this sideline. And this galaxy is up here in this pearly plot. It's one of these very, very bright galaxies with a high degree of dust reddening and high metallicity probably. But we don't know. We cannot really measure the metallicity from this spectrum. It's too low resolution. And then the third example is also from the NOT and the VLT. So this spectrum I took myself. I happened to be observing with the NOT. And so we got a spectrum about half an hour after the burst with the alphosk, and then another one with the alphosk, and then a bit later we also observed it with the VLT. So this is, again, one of these where you see strong reddening, and you see the 2175 angstrom bump. But it also shows how important it is. If you can be there fast, you can do something with a smaller telescope, because obviously these ones quickly get fainter. This is the final example of this. This is another paper, another event. This is observed not with the NOT, but with the VLT X-shooter. So here we have something that is strange. So it's an afterglow that is not. We cannot fit it with the normal extinction curves we know from the local group, and like either the SMC or the LMC or the Milky Way. None of these extinction curves can explain this spectrum. So normally it would be a power law that would just go on, but you see this one drops very quickly, very abruptly. The redshift is 0.9 in this case, so it's around 3,000 angstroms or something like that in the rest frame, and we don't really have a good explanation for why it looks like this. So I think there are things to see there in this 40% of the afterglows. We don't have a lot of information about. That's something that needs to be studied. There's a lot of potential to find something new, I believe. The second example is very high redshift GRBs, and here I just want to say that they do occur, and this is one this is an X-shooter spectrum of one that came on the 5th of September last year. We're still working on that. So you see the strength of X-shooter. I mean, this is only the vis and the near infrared, but we have this very long baseline, so we can get a lot of information in this one go. With alphosk, it will stop here. So we really need to have this broad wavelength range at the same time. And in this spectrum, there is some indication that there is a roughly 20% neutral fraction, but we're still working on that in the IgM neutral fraction. So that seems to be showing that around redshift 6, between 6 and 7, we can see this change in the neutral fraction from being highly ionized to being neutral. That's what we want to see. What is that history? And then I just want to show two examples from the NOT, two recent examples. So this just to say that the NOT is big enough for this. So we can use the NOT for this kind of work. This is a spectrum we took. Jonas took it actually, I think. He took it on New Year's Eve this year, just the last New Year's. Actually, I should have been down here, but Jonas observed it. I couldn't because of all the COVID. So this is a spectrum that was taken, I think, 14 hours after the GRB with the NOT showing this is redshift 4.6. So this is clearly something you can do with the NOT. It's a alphosk grism 20. So here we use a radar sensitive grism. Very nice spectrum. We still, so you can see we can get a very, very precise measurement of the amount of neutral hydrogen. We can also see which metals are there, but we cannot measure the abundance. It's too low resolution. And we can say it has very little dust. That's what we can say in this case. Then there's a new example. That's a spectrum taken by Tapio. He got quite annoyed. We're sorry when we trigger you. We're busy with other things, but but we really love this. So this is a redshift 5.6 spectrum that was taken just 3 weeks ago. So this was taken 45 minutes after the burst. So it's clearly something that is within the range of the NOT. We can do that. And then I would like to mention, we briefly talked about it before the coffee break, fast response. That's clearly also something we would like to do with for gamma ray bursts. So this is the example Michael mentioned for using the rapid response mode with the VLT. In this case, it was taken about 10 minutes, first spectra were taken 10 minutes after the burst, and then there was a sequence, and you can see the response of the interstellar medium in such a galaxy to the light from the afterglow. So you want to study the change of absorption lines as a function of time after the event and see how the interstellar medium is responding to this flash of light. And that gives you, of course, new information about what is the distances and what is the densities and so on. There's a lot of information you can get out by going into this time domain and see the change of the absorption lines. And with the VLT, I think the record is 10 minutes, and we think with the NOT we can do at least within 2 minutes, we heard. So that there is a space there for doing something that has not been done before. And I think that's something we should really try to secure. Explore something that has not been explored before. We can do that, so we should do that. Then I just want to say a few words, and then I have to stop in a second. Quasars, it's the same. I just want to mention that there's some very nice posters of Marina, Johannes, and Gotchen, if I pronounce it correctly. Please, and they will say a few words soon. But it's basically the same. The information you're after is spread over a long span of wavelengths, and what we have to do small chunks at a time. With the NC, we can get much bigger range at the same time. So that will give a strong edge for. There's also reddening issues we are trying to understand with quasars. So that I think also for that it will be a great instrument. I'll skip this one and then I will get to the last slide. So what I want to say is that we are trying to build, in some sense, a dream instrument for these science cases we have here. So I think it will be a dream instrument. Will really be. Certainly, it's my dream instrument. But it will also be not only my dream. I hope I made that clear. I don't want it to be just my dream instrument. I want it to be everybody's dream instrument. I want it to be something everybody will feel. This is something that is giving them an edge for what they want to do. And then, of course, we have to get to the problems. So that's why I gave it the title Odyssey. I think it really is an odyssey. You know, story of Odysseus. We know the Greeks. They will correct me when I'm wrong. But you know, he lost men to monsters. We also lost men to monsters along the way. And sometimes it seems like the gods are against us. But then again, other times it seems like manna is falling down from the sky. I know it's another story, but I guess you get the picture. And it will be completed. I mean, like Odysseus, we will get home. I mean, I am absolutely sure about it, but it's just difficult. It is a very difficult task we have, and much more difficult than we realized when we started, we have to say. But I think it will be, and it's not long. And when we're done, I think our community will have an instrument that is really will give us some competitive edges that will make us do things we cannot do, and will make us. I mean, I listed what I think, but we'll hear that from Michael now. What all the great things are. Thank you. That's what I would like to say.